Okay, we're going to finish up our gravitation notes by first talking about escape speed. This is a really cool idea. The escape speed is the speed that an object needs in order to not be bound to a system gravitational anymore. So, for example, the speed you would have to throw something at from Earth's surface in order for that object to never come back down. Obviously, if we throw something, it usually comes back down. Even if our planes, they eventually come back down. We're talking about sending something so fast that it doesn't have to come back to Earth. Okay, think about like a rocket and or a space shuttle. Well, not a space shuttle, but a rocket, if we're going to the moon or something, has to escape the Earth's gravitational pull. So, in order to do this, to escape, the object must become unbound. And remember, the condition we talked about for bound objects or bound systems, gravitationally bound systems, have negative total energy. So we need the total energy to therefore be either greater than or equal to 0 joules. If the total energy, the kinetic energy plus the gravitational potential energy, is negative, that's a bound system. The object that's in orbit will eventually come back. If the object has 0 or positive total energy, then that object is unbound. It will not return. It will not be a nice, stable, closed orbit. That object will not return to the near the star or planet or whatever that it started off at. So find the launch speed necessary for a 28,000 kilogram rocket to escape Earth's gravity well. Gravity well is just a term basically for like the sphere of influence of the Earth where it will pull things back. So it kind of has this idea of if we are out of the gravity well, then it's unbound, meaning the total energy is at a minimum 0 joules. So remember that the total energy is the kinetic energy plus the gravitational potential energy. And at a minimum, we need this to be 0. So I'm just going to set this to be 0. Remember that the kinetic energy is equal to 1/2 mv squared. Gravitational potential energy is negative g little m big M over r. And then this, since this is 0 over here, 0 joules, we can just add this to the other side. We need, at minimum, the kinetic energy to equal the gravitational potential energy. That will ensure that the object will not remain in orbit, but will instead become unbound. It doesn't have to orbit anymore. So, what that's going to look like is this. 1/2 mv squared equals g little m big M over r. I have the mass of the little object here that's trying to get unbound. We're going to cancel that out. We're solving for v. Notice that, once again, the mass of the object that's trying to leave does not matter. It doesn't matter if this is a 28,000 kilogram rocket or a 1 kilogram baseball. Okay? They are going to have to find the same escape speed. Doing some rearranging, multiplying both sides by 2 and taking the square root, I see that escape speed ends up being equal to the square root of 2 times g times m over r. That's the escape speed equation. And again, this is something you should be able to derive. Just like the equation for acceleration due to gravity at any planet, just like the orbital speed equation, the escape speed equation you should be able to define this. And I'm just going to make a little note that the escaping object's mass doesn't matter. That's really cool. So, no matter if it's a baseball or a rocket ship, it has to move at the same speed as it's leaving Earth's surface in order to fully escape. As it goes up, as r increases, r again, the distance between the centers of the object, so basically the distance to the center of Earth, as it goes up, the escape speed needs to be less. But think about what happens as objects go up. They lose speed. Okay? So as the object leaves Earth or gets farther away from Earth, the escape speed decreases, but it's just a matter of making sure that the escape speed is always bigger than, or that the speed of the object is always equal to or bigger than the escape speed, and it will leave Earth. The bigger Earth is, the more it tries to pull objects back down, the greater the escape speed will have to be. But it's really interesting that the speed is the same no matter what the mass is. Now, the energy will be different. You'll have to give the object more and more energy if it's really big, but the speed it has to achieve will be the same. All right, let's actually calculate this. For Earth, let's see, 2 times 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Mass of the Earth is 5.97 times 10 to the 24th kilograms. And R is the distance between, is basically Earth's radius. Earth's radius, as we have seen before, not right here, is 6.37 times 10 to the 6th meters. Take the square root of all that. We get that Earth's escape speed is 11,181.4 meters per second. For an object to escape Earth's gravitational pull, to not be in orbit around Earth once it leaves, it has to be traveling that fast when it leaves the surface. Obviously, you can build up speed after that, but the escape speed will be a little bit less. The escape speed from Earth's surface is this high. Kind of an interesting concept. We're going to talk about orbital shapes now. Basically the shape and how what happens to an object in orbit can affect the shape of its orbit. So sketch a satellite in a circular orbit around a planet. Mark a point A where the satellite currently is. So here is the planet. We're going to draw a circular orbit around that planet. Okay, not bad. And we're going to say that the object, the satellite, is currently right up here. Sketch the orbit that would result if the satellite began moving slightly faster than it currently is A. It's in circular motion at point A. Okay, it's moving in a circle. And the reason it's moving in a circle, if you remember from circular motion, is it has an acceleration due to a force towards the center of the circle. That happens to be caused by gravity. It also is moving tangentially from that. It has some tangential velocity. So it wants to move in this direction, but it's feeling a force in this direction. It ends up being kind of moving in a curve. It gets pulled around this circle. So let's think, if that satellite, let's say it has some rockets on it. Let's say the rockets fire to make the satellite move a little bit faster as it's going to the left right here. What's that going to do to the orbit? Well, here's our original orbit. At A. If the satellite starts moving a little faster, it's like the tangential velocity is winning over the orbital velocity. It'll start to go out a little bit farther from its circular orbit. What that does is that means that it's not going to be as far away, or it's going to be farther away from this central point, this object it's orbiting, the planet, and that means the force is going to be less. It's not going to cause it to pull towards the center as much. So the object is going to move a little bit farther away. And matter of fact, it's going to keep moving a little bit farther away because the force on it is just not quite as much. Now, it's definitely losing speed as it goes out to here. But what happens is the orbit actually becomes bigger at all these points until it gets down to about until it gets halfway across its orbit. Now out here, it's definitely farther away, so the force is less, but since it's so much farther away, think about it. The gravitational potential energy has become, well, it's gone up, essentially. If the gravitational potential energy has gone up, that means the kinetic energy has gone down. The object is now moving much slower out here than it was here. So since it's moving slower, now it's almost like the force of gravity starts to rein it back in. The force of gravity, because it's not moving as fast here, it's not going to continue moving in this circular orbit. It's going to start pulling it back in. What we end up with is the orbit, or is the object, the satellite, kind of slowly starting to move back in towards its original spot. And actually, when it gets right back to where it started, or when it gets right back to the same place where it started, it's actually in the exact same spot. So notice what we've done. We've taken a circular orbit, and I know it's kind of tough to tell on here. We've kind of made it like an oval or elliptical. A similar thing happens if the satellite instead fires rockets to move slower at point A. If it starts to fire rockets to move slower at point A, then the tangential velocity is too slow, and it's going to start falling in towards the center of the orbit, because the force is going to pull it in. So it starts to move like this. Okay. And just in case you can't see it, I'll kind of make this a little bit more dark for you guys. It starts to move in towards the center of the orbit. Until it gets right here. Here, it's moving really fast because it doesn't have a lot of gravitational potential energy anymore because these objects are pretty close. The kinetic energy must be really high. The kinetic energy is really high, so the speed is high enough so that at here, the object starts to gain, or to go farther away. The force is really strong, but it's gained enough speed so that it's going to pull away from the object again. And again, it ends up back at A. again making an oval shape. So to sum up, what's happened in these two examples is if the rocket fires if the satellite fires its rockets to move faster, it's gaining kinetic energy at point A, and it's becoming less bound, which equals a larger, now elliptical orbit. Started in a circular orbit, now it's an elliptical orbit. But the key thing is it still returns back to the same spot. Down here, the rocket is firing in the opposite direction. To slow it down, it's taking away some kinetic energy. It's becoming more bound. The total energy is decreasing, which brings it to a smaller, a tighter, more elliptical orbit. But once again, it still ends up returning to the same spot because at this point it's now moving much faster, and the force of gravity isn't strong enough to keep it, kind of spiraling inwards, so it will start to move back out, and it will still end up back at A. So this is really interesting. You have to be really careful if you're trying to change the orbit of, let's say, a satellite or a spaceship. You have to actually do it in a couple different stages because of how the orbital mechanics work. And if you go to, if you go and work at somewhere like NASA, they have to calculate all these different orbits. They have to figure out exactly how to fire the rockets or whatever to figure out exactly how to put these spaceships and satellites and probes into different orbits. It's really fascinating stuff, to be quite honest. A lot of math that goes into it. I always thought that was really, really neat. Finally, so you'll have a couple of questions about orbital shapes. Let's get down to talking about angular momentum. Now, we talked about angular momentum in our last unit, and the reason we saved gravitation for last is so that we can talk about angular momentum in gravitation as well. You know from the beginning of the year that if an object or system has no net force on it, then that means that there will be no change in the object's momentum. In other words, delta P equals 0. Well, as we did the rotation unit, we saw that all the rules that we had learned so far also applied to objects in rotational motion. It's just that the variable names changed, and there were some corresponding variables that weren't exactly the same, but were similar. It's true that if there's no net force, then the object's linear momentum can't change. It's also true that if the net torque on an object is 0, then there is no change in the angular momentum. And that symbol is L. And the units are kilograms times, I think, meters squared over seconds. All right, and that's just the rotational equivalent of linear momentum. For any orbit, it is true that there is no torque on the object that is in orbit. Let me show you why. So there's no torque on orbiting objects because the equation for torque is RF sine theta. F is the force, R is the vector that goes from the axis of rotation to where the force is being applied. The force on A is inwards like this, but R is outwards like this. Those are anti-parallel. They're not in the same direction. They're not parallel, but they're anti-parallel. So since R and F are anti-parallel, theta is equal to 180 degrees, so the sine of 180 degrees is 0, so the torque must be 0 Newton meters. So there's no torque on an object that is in orbital motion, that is in orbit around something else. That's really powerful. That's really, really important. What that leads to, if the torque is the same, that means the angular momentum cannot change. So, angular momentum is conserved. And if the angular momentum is conserved, that tells us that L equals L naught. And since we learned that the angular momentum for a point object is equal to mvr, where m is its mass, v is its linear velocity, and r is its distance from an axis of rotation, then it stands to reason that since L equals L naught, mvr equals mv naught r naught. This statement of conservation of angular momentum is useful for any object in orbit, but it's especially useful for objects that are in non-circular orbits. The reason it's important for those is because if they're in non-circular orbits, we can't use centripetal force to figure out how fast they're moving, but we can use the conservation of angular momentum. In the diagram to the right, a planet of mass 5 times 10 to the 23rd kilograms is in a very elliptical orbit around its star, as you can see. If the planet moves at a speed of 7.3 times 10 to the 3rd meters per second at A, which is a distance of 8 times 10 to the 10th meters away from the center of the star, what would its speed be at B, which is 3 times as far away? Well, we can't use circular motion here because this is not circular motion. It's elliptical motion. It's motion in an oval, well, more technically an ellipse. But since we know angular momentum is conserved, we can say that the angular momentum at point A is equal to the angular momentum at point B. LA equals LB. MVA RA, mass times the velocity at A times the distance from the planet to the star at A. We're pretending this is the axis of rotation. Not pretending, that's what it is. Equals MVB RB. I have m's in both equations. They will cancel. I'm left with VA times RA equals VB times RB. I know how far apart or how far away from the star the points are at A and B. I know the speed at point A. I can find the speed at point B. The speed at point A is 7.3 times 10 to the 3rd meters per second. And that's getting multiplied by 8 times 10 to the 10th meters equals VB times 3 times as far away as it was at point A. So that's 3 times 8 times 10 to the 10th meters. Now wait a sec, I have 8 times 10 to the 10th meters on both sides. I'm just going to cancel those out. And to get VB by itself, I'm just going to divide this by 3. VB ends up being 2,433.3 meters per second. And that's how we can find the speed of an object when it is in elliptical motion, when it's orbiting in an ellipse, not a circle. Okay? There's everything you need to know about gravitation. It's a fun little unit. I like it as a good way to review things as we close the year. If you have any questions, please let me know. I will talk to you later. Goodbye.